Okay, so now we are on the record. Well, this is Jose Manuel Barrientos Lopez. I am from Purdue University. I'm a graduate student. I was a participant on Goals on 2023. Uh, it was a very important conference for me to attend. I get completely engaged to the field that I have already started to study at the moment. But getting in touch with the active community in research was very important for me. And at that time, I was not a student in Purdue yet, but goals was very important too for me to get decided to pursue a PhD abroad. I am originally from Mexico, and when I went to goals, I was still in Mexico, and well, I ended up in Purdue, um, and I'm very happy here learning about operator algebras. I am working in the sister algebra side, and this talk will be about irrational rotational algebras. I hope you get something from it. Um, so first things first, I would like to thank to the organizers for the tremendous effort that they put into this event, um, with all the difficulties and whatnot. But we are here learning. Uh, Thanks to the lecturers that take their time to prepare very good material and notes and presentations, and they have made it easier for the newcomers and the interested people in the field to get fascinating with the variety of things that we can study here. And to all the new goalies and the ones that are here and the ones that will watch this asynchronously, welcome to the community. I hope you enjoy the trip. Okay, so this will be the structure of the talk. I know that yesterday you saw a dynamical approach to the irrational rotational algebras. That will be not my case, just for one small reason. It's because I first read Davidson's book and then I read Dana Williams' one. So the first way that I learned to approach to rational rotational algebras was the universal property construction. So we are going to see a set theoretical definition. We're going to prove the existence of rational rotational algebras. Then we will study what happens in the commutative case. We will check some averaging properties and check some completely positive maps that exist in the algebra, tracial states and whatnot. And I will give in one slide the scratch of classification, just because I don't think there will be enough time to get there. Um, so we will start with a canonical realization of the object. So let's pick a real number R and consider the one-dimensional torus with this identification. Yep. And let's fix a Hilbert space, the L2 of T, and define a couple of operators. We'll denote it by U and V. Um, they are given as follows. So U is multiplication by the identification on the torus. So we are moving the argument, and V is a rotation by theta on the torus, right? And the following is an exercise. You will see lots of exercises because I believe most of them they are very computational, and they'll get you in touch with the structure and the secret behind the sister algebra structures. So these operators are unitaries, and they satisfy this relation that I will be denoting by, I will be calling it back with one. So U and V almost commute. Okay, they differ by a constant that is unimodular. So this constant omega is 2 to the 2 pi I theta. Okay, so it's a rotation by theta in the unit circle. Of course, if theta is equal to 0, and I'm talking about general case of unitaries satisfying this for theta equal to 0, we have commutative unitaries, but we we'll have a time to check that. So this is the main relation. Of course, U and B being unitaries impose another couple of relations, that is U star U equals the identity equals U star, and similarly for B. And they are also another family of relations, but I assume they are satisfied when I say unitaries. So in reality, I have like 6 relations, but this one is the one that is not uh, doable with words. So our goal is to study the largest C-star algebra generated by unitaries where the relation 1 holds. Okay, so this is just an example of 2 operators that make the relation hold, but we don't know if there are some other operators, maybe in different Hilbert spaces, that also satisfy this relation. So that's what we're interested in studying. And there's where the definition starts. So we say that A theta is a universal C-star algebra for 1, and I write theta, a dependence on theta, because 1 depends on theta too, if, and there are 2 conditions, A theta is generated by 2 unitaries, U and B, that satisfy the relation, and there is this universal property for any C-star algebra B that is also generated by unitaries U and V. And note that I am using small u and small p, just to make emphasis that it might be the case that we have them in an abstract C-star algebra, but after GNS we'll be able to realize it. But the general setting, we can think of this on an abstract algebra. They satisfy 1, and I will be able to map with a star homomorphism from A theta onto B, mapping generators to generators, and that is it. Okay, so this is the universal property, and let's have a little remark. When I say that an object is generated by a family, I'm meaning that the linear span of this family of monomials is dense in the norm of A theta. Okay, so I'm closing this span and I'm calling that A theta. Notice that the powers of U and B are allowed to be negative because they are unitary. So I have inverses and they're just the involution. And the definition is a universal property. So when we are facing a universal property, it's not obvious that there exist objects that satisfy the universal property. So that's the first theorem. There exists a C-star algebra generated by unitaries that is universal for the relation 1. Okay? Let's see the proof. For the proof, let's consider this family of pairs of unitaries in V of H for some Hilbert space H. We can take it all separable. That might be a good exercise to check why the Hilbert space can be taken separable. And the pairs are also reducible. That means that they don't satisfy any other relations between them, and they satisfy the main relation 1. And by the motivation or the concrete example in L2 of the torus, we know that this family is not empty. And I will take the direct sum over this family as elements in the Hilbert space, in the bounded operators on the direct sum of all this Hilbert space. We know that this algebra of operators has the norm, given by the supremum over all the family. Just finally, many of them are non-zero, etc. And I will set A theta to be the C-star algebra generated by this U and this V. Okay, so the spirit of this is that I'm exhausting all the possibilities when I'm taking the Greer exam. This is huge, and I will verify that A theta satisfies the universal property. So of course, U and V are unitaries and satisfy 1. It's a good exercise for you. It's a small computation, and if V is a C-star algebra generated by unitaries U and V that satisfy 1, I just need to convince you guys that it's enough to check that any map given in this fashion will be automatically continuous. Okay, so now that I have a candidate for A theta and I have another algebra B, I just have to check that a map given in this fashion is automatically continuous. Uh, with first given in these monomials, I can extend by by linearity, and now I claim that this is where the analysis meets the algebra. I want to show that phi can be extended to all of A theta. And for that ending, I say that it's enough to check that phi is contractive when it acts on polynomials. Okay. And here I am taking the same polynomial that I'll take before, but the variables now are u and v. These are like Laurent polynomials in some sense. And why is it enough? Because if phi is contractible, that will imply continuity. And then by the density of the polynomials, I'll be able to extend to all of A theta. And the heart of the proof is to use the tools that we have been developing in Go. So let's start with a polynomial, and let's take V to be the evaluation on u and small b on the same polynomial. But now this is this is a polynomial in B. And by GNS construction, there is an irreducible representation. I'm calling it pi, that goes from B to some algebra of operators, in some Hilbert space, and it is an isometry. Okay? Pi evaluated on B on norm is equal to the norm of B. And if we pick u prime to be pi of small u and v prime to be pi of small v, these are a pair of operators that belongs to the family C. And therefore, I will be able to compare the norm of these operators when I'm evaluating in a P. This is what I'm doing here. With the universal norm that I have on the direct sum given by u and v, where they are the direct sum of all such operators. And this first part is just algebraic, since I am defining phi at the level of linear combinations. I just split, and by definition of phi on the generators, I'm just switching generators in the same polynomial. And then the second step is just using that pi is a star homomorphism. So indeed, phi is contractive on polynomials. Therefore, it's continuous, and I can extend it to all of A theta, and therefore A theta is a universal object, the universal C-star algebra. When theta is not rational, A theta is called the irrational rotational algebra. There is a small typo here. Should have included irrational. But of course, if theta is rational, it is called the rational rotational algebra. But I would like to make this couple of remarks. This construction is valid for all theta, and we will see a contrast with the irrational case, from the irrational case to one rational case, the case theta equals 0. The study of the object has been done too for the rational case, but don't quote me here. I believe it's more difficult. The structure on the irrational case is a little bit more rich. It allows you to move move more stuff with the tools that we have at hand in the elementary sister algebras theory. And we will see now the commutative case theta equals 0. So the relation 1, and here we need to forget a little bit about the case, about the first realization of the u and v that I presented. Here, let's just consider two unitaries in some Hilbert space that satisfy the relation 1, but for theta equals 0. So it becomes a commutative relation. UV is equal to VU. And therefore, the sister algebra that they generate is abelian. Okay? The generators commute, sister algebra will be abelian. And we claim that in this case, A0, which is A theta, but theta equals 0, is isomorphic as sister algebras to C of T2. So by Gelfand-Neymark, A0 is isomorphic to the continuous functions on its, its spectrum, the Gelfand spectrum, I think we call it. So it's enough to show that the Gelfand spectrum of A0 is homeomorphic to T2. So we are reducing the problem to a topological problem. Any character will be defined by its action on U and V, and their mappings will be also unit numbers, unit complex numbers, because phi preserves the properties of being unitary, being a star homomorphism. And also, any pair that I take in the two torus generates a sister algebra, this subset of C. But the important part here is that by universality, there will be phi such that sends operators to operators. And that's all what I need. Now, this is an exercise. The mapping going from the characters to T2 that sends phi to phi of U and phi of B as a pair is an homeomorphism. And this is an exercise, and it's enough to check that it's continuous. And you have it is homework to argue why this is enough. So some properties of the abelian case. First of it is an algebraic property. C of T2 is not simple. Indeed, any set of this given in this way is a non-trivial ideal for any E closed subset. And as a contrast, if theta is not rational, A theta is simple. Okay, and before proceeding with the properties, I just want to give us some information that C of T2, A theta is also called the non-commutative tori. And this is, part of the origin that when we are in the commutative case, we recover the continuous functions on T2, okay? So when we do not commute, we do not have access to this topological space of non-commutative topological space of two torus, but this is its algebra of operators. Okay? So that was like the small thing that I wanted to say before the second property, that is analytic. C of T2 has infinitely many traces. Of course, the integration against any Borel probability measure defines a trace on T2. However, for the irrational case, A theta has a unical partial faithful state. And the tier one is a topologic property. C of T2 has no non-trivial projections. And, it's formulated in terms of an algebraic object that are the projections, but the proof of this statement is just topological. So that's an exercise for you. In contrast, there are infinitely many non-trivial projections in A theta. However, I don't think we will have time to talk about this fact, but of course, I'll send you the references. So following theorems are a consequence of the dynamics on the generators. Okay, What I mean by that is that if I take a pair of unital complex numbers, complex numbers with modulus equal 1, uh, the pair uh, the pair lambda u comma mu v satisfies the relation 1, and the sister algebra that they generate is exactly a theta. Why? Because we are just rescaling the generators, right? So we can put the constants in front when we take the linear span, and we end up with the same sister algebra. So by universality, there exists a mapping from a theta to a theta, such that sends u to lambda u, v to lambda to mu v. And as an exercise, this star homomorphism has a two-sided inverse. And so what we are in reality checking here is that this assignment, that for any pair on the two torus gives you rho of lambda mu, defined in the universal sense, is a canonical dynamics that is encoding symmetries. I have a map from a topological group to automorphisms in a sister algebra. And this should ring a bell with respect to what you checked yesterday in the sister dynamical lecture. Okay. So this encodes symmetries on generators. And let's check some byproducts of the dynamics. And for this purpose, let's check this lemma. So take an operator in a theta and define this map. The map is going from T2 to a theta, and it gives just the evaluation of rho lambda mu on T. And this map is indeed norm continuous. And in particular, if we pre-compose, entry-wise with rotations in the circle, we obtain continuous functions again. Remember these definitions, especially g of t, because that's the one that we're going to work with. The second one, it's the same, but I'll be focusing more in g of t. And the proof is an exercise, but the idea is very simple. You first check on polynomials. So take a polynomial t on a theta and show by means of this equivalent property of continuity that this norm will decrease or will go to zero if we approach to the point of evaluation. So it's very algebraic, and once that you have the proof for polynomials, you'll be able to extend it, by density to the whole of elements of a theta. And this continuity is important because we can make sense of the following definition. So take phi1 and phi2 map, and I'm saying it's just a map from a theta to a theta, given in the following way. Yeah. So yes, I am taking an integral of a continuous function, but I'm claiming that this takes values on a theta. So what's happening here? Yeah, integrals are always a mess. So this is g of t. Remember, I'll go back a little bit. G of t was for a given operator on a theta, we fix the first generator and we move the second one. Okay. So this is it. So yeah, integrals, but don't be scared. Let's have a small crash course on integration of continuous functions that takes values on complete norm spaces. So take a uniform partition of 0, 1, set these partial sums. Okay, I'm taking the evaluation of g of t in the ending points of the partition. I'm taking
just like Riemann sums then?
Yeah, it's just Riemann sum. So the fact that gt is uniform continuous on 0, 1 will ensure that this sequence Rn of t is Cauchy in A theta. And this is an exercise, but it's exactly the same as in the classic Riemann integration case. And this completeness or this Cauchiness will give us the existence of a limit in A theta. We just call the limit phi1, and we use a notation given by integrals, okay? And we do the same for phi2. And yeah, the fact that someone say something gives me like space to say this. This is a good moment for questions. If you have any, hit me up. Otherwise, I'll continue. Okay. So this is the crash course on integration. This is what we are doing. And with that integrals at hand, with the definitions of phi1 and phi2, we have this theorem that I will state just for the case of phi1. Case for phi2 is analogous. But phi1 is positive, contractive, idempotent, and faithful. Something cool that I am the last or the very last lecture on sister algebras is that I can use all these words without stating the definition because that was already covered. So I'm very happy in that sense. For all continuous functions on the torus and for all operators in A theta, I have this factorization property. So it doesn't matter what happens on the continuous functions C of t. I just care about what's happening in A theta and I put the other ones outside. The third property is that the evaluation of phi1 forgets the second generator, okay? And hence, when I take the image of A theta under phi1, I just get the sister algebra generated by U back. Okay, so it completely forgets about the second generator. And if you put property 1, property 2, and property 3 together, you have something that is called a conditional expectation from A theta onto C of t. So that's very important. We are obtaining not only a conditional expectation from a sister algebra onto a subalgebra, but onto a commutative subalgebra, which is not very common. And the last property is that when theta is irrational, we have this limit interpretation of phi1. So I am in reality taking a kind of average, okay, and that should be that is consistent also with the concept of integral. Integral as a Riemann sum is some kind of average, but also an expectation gives you a notion of an expected value, right? And here we are taking nothing but an average of evaluations of compressions of the operator by one of the generators of the algebra. And when I say that the case for phi2 is analogous, I mean that if you change phi1 for phi2, in the other things you have to change u for v. Okay, so here instead of f of u, I will have f of v, f of g of v, and whatnot. Sister algebra generated by v that turns out is also isomorphic to c of t, but that's the spirit of this case being analogous. So let's check the proofs or some ideas. So to check that it is positive, we start with a positive element, and then since g of t is a star homomorphism, it preserves. No, I'm sorry. This is preserved by. This will preserve the positiveness of t. Okay, g of t for all small t, and hence all these sums will be positive as well. And therefore, when I take the limit, and I stated before that the limit of these Riemann sums is just is the integral, then the set of positive elements, and since the set of positive elements is closed, I obtain that the integral is positive as well. To check that it's contractive, you need to check that gt of t is preserves norm, okay, for all small t. And this is because this guy, g of t, evaluated at small t, is a star isomorphism. You remember it has like this rho sub 1 comma e to the 2 pi. Yeah, that's star homomorphism for all t. And hence, when I take the, how's it called, the triangle inequality on the Riemann sums, I do not exceed the norm. And in the limit, I keep under the norm, keep myself under the norm. Idempotent, and this means phi1 equals phi1 to the power of 2, is an exercise. To check that it's faithful, I'm also giving you just the scratch. You use Hambanack. Given a positive operator that is not zero, use Hambanack to find a state such that when I map 0, 1 to C by means of the precomposition with the state, I obtain a positive continuous non-zero function. And again, Riemann properties, Riemann integration tells me that the integral of a continuous positive non-zero function is non-zero. And since eta is a state, I will recover phi1 of t non-equals 0. Okay, that's faithfulness in this context. The second part is that the factorization property that's called also being a CT bimodule property, but that's just terminology. I like calling it factorization property. So the first step is an exercise. You convince yourself that the spectrum of U is exactly the two torus. Okay. This is a very, very nice exercise. Makes you think about properties of spectrum and topological properties. Therefore, the C-star algebra generated by U is exactly or is isomorphic to C of t. And since this function evaluated at U just remembers what it does to U, by definition, we get that G of t, gt of small t is exactly the identity on C-star algebra generated by U by the continuity, okay? And since it is the identity on the generator, I extend to continuity and by density to all of the family. And thus, since I can see these two elements, f of u and g of u, this is functional continuous calculus. I can see these two elements as elements of C star of u. Then again, using the Riemann properties of limits, I'll be able to factorize, this guy and this guy at the algebraic level. And then by continuity, I can put the limit inside, and I already left apart f of u and g of u. And this is just coming back to the original, or to the definition of phi 1 of t. Okay, so I like these proofs because, this is what many times in operator algebras we do is sometimes we cannot manage the whole thing, but we can do, some progress in the algebraic sense, at the finite dimensional level sometimes, or finite sets sometimes. And in the limit, we have a nice behavior and continuity do the work. So this is an example of how, that situation is reflected in this case. The part 3, which was, that it forgets the V on linear combos is an exercise tool, but you just have to check it on monomials and use density again. And the part four, and let me the part four, let me show you the part four again. Sorry if this, yeah. Part four is this limit identity. It takes a little bit more, but roughly speaking, what this property, what the proof does is it uses theta being irrational, because when we develop like the limit, the partial sums or the finite partial sums of the limit that we want to evaluate, and we end up with a factor that not all the times converges to what we need to converge. Just converges when theta is irrational. So you can go see Davidson. He does it well. Uh, and I myself have, all these computations made, with high high detail. If you need them, just hit me up. But let's keep going. Some other properties. When theta is irrational, then phi1 compose phi2 and phi2 compose phi1 are the same thing. Okay, so it doesn't matter if I first forget one generator and then I forget the other one, I will recover the same element on a theta after evaluation. Okay, so this is very dynamical. Yeah, I want you to I want you to have you this ringing a bell with dynamics. Okay, so, and also if you consider this in the sense that P1 and P2 are integrals, you remember that if you have an integral in one direction and an integral in another direction, it doesn't matter what direction you take. This is like elementary integration on Calc 3. Okay, you can sum first in this direction and then the other one, and Gauss showed that that was the same. Well, we have the same situation here in the non-commutative version, I'll say. So if I called this composition phi1, phi2 as tau, this is a property. Tau takes values on C, so scalar multiples of the unit of the identity, and it is a faithful threshold state. And the fact that it takes values on C is a consequence that on monomials, if you evaluate linear combos on V, you forget about U, and then you take that linear combo and you forget about V with the other operator, you end up just with coefficients. Okay? You don't have anything else but coefficients. You already forgot the generators, and that's why this is complex valued in some sense. But being faithful and threshold state is also very important, and it can be verified in the same fashion as before, as described earlier. And this is contrast with the rational case, or at least with the case theta equals 0, is that tau is a unique threshold state on a theta. So for the proofs, I didn't include these proofs, but you can go see Davidson's. It's again the same spirit. You check properties on monomials, you extend by continuity, and yeah, and that is it. Yeah, and of course the third property, it's one of those where you will use the first one, but also you suppose there is another threshold state, and you check that they are mapping exactly the same thing. So this is the main theorem of this presentation. So what I have in this theorem is that in the irrational case, A theta is simple, and I have small proof for this. So take a non-zero ideal I subset of the theta, and take t to be a non-zero element in the ideal, and it's also positive. Okay, it can be an exercise to check why such elements exist. Okay. The limit formulas for phi1, or let's say phi, show that phi keeps I inside I. And why is it true? By the limit formula, I mean this one with the 2n plus 1 summands. So in that case, since t is in an ideal, the inside of the summand is also in the ideal because I am multiplying by t, and therefore the whole sum is in the ideal again. And when I take the limit, I keep myself in the ideal because ideals are closed. Hence, the evaluation of t on tau is an element of the ideal, right? And thus, the ideal contains a non-zero scalar, okay? Since tau of t is it's scalar valued, I have scalars in the ideal, and the scalars that will implies therefore that the identity lies in the ideal. And when that's the case, the ideal has to be all of
All
A
of
theta.
A theta, yeah.
Exactly. Okay. So this proof is very transparent. Yeah, I like it very much. But yeah, to check the existence of a positive element in I that is non-zero, it's a small exercise. You know, it reminds you just the definition of ideal, some small properties, you know, and that is it. So the path to classification. Here is where I have absolutely zero detail, but if and I still have, you know, like 15 minutes. So let's do this. I'll explain kind of the spirit of the classification, and time permitted, we can switch to the tablet or solve some of the doubts that you have. But it is possible to embed A theta into an AF algebra, okay? And this is very strong. This embedding, or the first constructions, are not easy at all. They are very, very weird, yeah? So we have to construct an an AF algebra with with the irrational theta, okay? So let me scratch in here. Please let me know if at some point you stop seeing what I am doing. So I will write something here. So given theta, okay, I can write it as a limit of a continuous fraction. Okay, so I have 1 divided by 1, a1 plus, 1 a2 plus da, and it ends on n, right? And this is because this guy is irrational. It's a continuous fraction. Okay. And these numbers, A1, they satisfy a certain property of
Do you want like a not hanging out before that too? Because then you'll get a whole number point, blah, 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 encompassing all of the irrationals.
What was the first thing that you said? I think
What I mean is this fraction here, isn't it only going to be like a decimal? So if you want to put in like a naught added to this to
yeah,
give me
yeah, sure. Yeah, sure. Yes, I want this to be the representation of the irrational number in terms of these fractions, these continuous fractions. Yeah, so I need an A naught at some point.
like right after the limit to it's or yeah, or after this, yeah.
Yeah, I I'm not sure if we need it right now, but
You could just restrict to the rational between 0 and 1, and then this will be
oh
fine.
yeah, completely yeah, I agree. Yeah, that solves the problem. Thank you. So if we take theta in this case, these numbers A1 satisfy, a recursive relation that is given, I don't really remember very well the details of the recursive relation, but it is given in terms of, I think it's something like this, an, bn, uh, wait a minute, it's like qn plus 1 is equal to an qn plus or minus, no, it's plus qn minus 1. And this is for uh, bn divided qn being equal to the nth continuous fraction. Okay. So a similar property follows for P, and with this in mind, we'll construct an AF algebra, and the AF algebra is given in the following way. So Bn will be equal to Mn Mqn plus or direct sum Mq and minus 1. Okay. These are AF algebras. I'm taking coefficients on the complex numbers. And the good thing here is that when I do the embeds, Bn, when I have finite dimensional algebras, I have to specify who are the embeddings. And the embeddings are the ones that will bring theta or these expansions to the game. So I take Bn mapping by beta n to Bn plus 1. Yeah. And the embedding, and I'll follow here. The embedding is given as follows. I'll take A direct sum B, and I will send it to the diagonal that has, what has a diagonal? It has A, and A has it AN times, yeah. Then it has B, and then it has another copy of AN, of A, I'm sorry, yeah. So this, you can verify that these guys will have the right dimension. And the fact that they have the right dimension is because the recursive property that defines the QNs have the right dimensions. Okay, so verify it has the right dimensions. Right dimensions. Okay. And I take the inductive limit of this sequence of finite dimensional sister algebras with connecting maps beta. I call that limit, let's say, AF theta. This is the inductive limit. Slim of the system Bn, comma, beta n. And the non-trivial result here is that A theta embeds in AF of theta. Okay? And you might be wondering, wait a minute, we do not know if A theta is itself an AF algebra. I didn't prove that. And of course, it is not true. And there is a nice property that allows to check that A theta is not an AF algebra. But let's go to the next slide. So this is the construction of the AF algebra that receives A theta, that has A theta as a subalgebra. And this is not possible if theta is rational. This is just possible if theta is not rational, when it is irrational. Why? Because when I am, when I see like this guy inside the AF algebra, the injectivity is given by A theta being simple. And if theta is not rational, A theta cannot be simple. That's another amazing exercise for you to try. I will give you guys like a list of exercises with, the statements, so you don't have to be checking on the video or your note what I say that was exercise. I'll write it down. I'll send it to the server. But when theta is irrational, A theta is simple, and that's a necessary and sufficient condition. If theta is not irrational, then A theta cannot be simple. And that simplicity or non-simplicity is what messes the embeddability of the irrational case in this particular of the rational case in this particular AF algebra. Okay. Yeah. And as I wrote, I hope I didn't mess like the following the next slides, but please let me know if you see something weird. So the result of embeddability is highly non-trivial, and it deals with finite dimensional approximations technique that is called the Berg technique. It's okay. Well, I won't say this because I'm being recorded, but when we finish the recording, I can say what I think of this technique. But it's a very elemental technique. It's easy to prove that the technique works. It's a functional analysis fact. And it's very surprising that it gives you this kind of embeddability. Just it's very, very difficult to write down like the construction. And it also uses, AF and embeddability is a great paradigm nowadays in classification results. Like this paper by Christopher Schaffhauser on simple subalgebras of AF algebras uses, exposes this technique, and it was like one of the first steps that he take when he realized that the secret behind the classification problem was to check on the ultra powers and whatnot. Well, that's another application on these great techniques of that lead to the latest result by many hands on the classification of nuclear sister algebras. But yes, this was actually one of the first times that someone tried to embed a theta into an AF algebra. This is work you Pimsner, Voiculescu together, and Riefel also work. He used the work by Pimsner and Voiculescu to complete or to have a first approach to classification of A theta. So this embedding A theta into an AF algebra is good because we will have a group isomorphism between the K theory of A theta and the K theory of the AF algebra. And this is where I ask you, like, why we don't know, why cannot use the K theory, just the K theory of the AF algebra to classify A theta, which will be possible if A theta is an AF algebra, is because K1 of A theta is non-trivial, is Z2, like, direct sum of the integers. And I think you saw that the K1 group of an AF algebra has to be zero, okay? And that's invariant. So since the K1 group of A theta is not trivial, A theta is not an AF algebra. But even though we don't have A theta to be an AF algebra, we can use the group isomorphisms that the K theory induces, and that group isomorphism uses, this thing that I told you before about projections on A theta, that there are, enough projections to be able to manipulate the traces and what's called, and the K0 group, with success. And the fact that the Elliott's classification gives control on the AF algebra and its traces allows to find the criteria to classify irrational rotational algebras in terms of the parameters of rotation. And these two algebras will be isomorphic if and only if their angles differ by an integer. And here there is a small typo. It should be plus or minus eta. Yeah, it's not. It's not about eta, but also the negative part. So I want theta to differ from eta or negative eta by an integer. And that'll be necessary and sufficient for the associated irrational rotational algebras to be isomorphic. This result was due Riefel, I believe. The problem of the powers on A theta is a result by Riefel and powers, and the embedding is just an achievement by Pimsner and Voiculescu. And this is from the 70s and 80s, and those were the first steps that were giving results for the classification, and eventually leads to the conjecture of what the classification tries to do on nuclear algebras. But I think I'll stop here. This was almost 1 hour talking, and that was also everything I prepared. I had, the small addendum with the construction of the AF algebra, but other than that, I think that is all. Thank you very much for being here. I hope you had enjoyed the lectures. You are still left with the von Neumann algebra lecture, but this was all for sister algebra. I believe we should have a full week for just this example instead of 1 day. But yeah, I'm pretty happy to be here, pretty happy to talk to you, and this was the end. Thank you very much. So
Read from right to left.
yeah. Before proceeding with the questions, I will stop recording. So if there is any question, of course, but I will just finish it.